Hello, everybody. This is Mr. Fasoni. We're going to be continuing our journey through Chapter 1 about linear functions. And we are moving into Chapter 1.4, which is about solving linear systems of equations. So it's a little bit of a departure from the transformations of functions that we did before. This is also another skill that will be important in later chapters because we need to learn how to work with multiple equations at the same time to solve for common variables. So our goals for this section are to visualize solutions of systems of linear equations in 3 variables. That's a minor goal. And then the major goal is to solve systems of linear equations in 3 variables algebraically. So we're going to be doing a lot of manipulation of equations using what we know about keeping both sides of the equations balanced and using those arithmetic skills to knock out variables to solve simpler versions of linear equations, which I'll talk about in a few minutes. So first off, let's talk about visualizing these systems of equations. So a linear equation in 3 variables, or 3 variables in this case are going to be x, y, and z, is an equation in the form ax plus by plus cz equals d, where a, b, and c are not all 0. What they mean by that is, as long as one of the 3 variables, or one of the 3 values, a, b, or c, is not equal to 0, it'll work. So you could have something like this, 3x plus 5y minus 7z equals 10. That's a perfectly valid equation. You've got your a value, your b value, and your c value, as well as your d value. Or maybe b and c are both equal to 0, and you could also have an equation like this, 3x equals 9, where only the a value is there, and the other 2 values are 0. This could still be part of a system with 3 variables, but technically only one of the variables is showing. So the solutions to these systems are expressed in the form of ordered triples, and an ordered triple is just like an ordered pair. An ordered pair, like we graph, we could have 1, negative 5. To the right 1, down negative 5. Well, in a 3-dimensional situation, we could have the same type of thing. We could go over 1, down 5, and then, I don't know, maybe in by 3 if we're thinking 3-dimensionally. I'm not going to make you graph 3-dimensional systems. That is hard to do and hard to visualize on a 2-dimensional piece of paper. We might look at a few 3-dimensional graphs using software, and I'll actually pull some up in Algebra, which is similar to Desmos, later on in this lecture. Okay, so first part of the concept is done. Next up, there's 3 pages to this concept. The graph of a linear equation in 3 variables creates a plane. And just as a review, remember from geometry, a plane is just a 2-dimensional object. It's like a flat piece of paper that goes on forever. Recall from geometry, we've got some building blocks that we built everything out of in geometry. Point is what we would consider a 0-dimensional object. It's just an infinitely small point in space. If you take that point and stretch it in one direction, that creates a 1-dimensional object, which would be a line that goes on forever in a single direction. And then if you stretch that line perpendicularly, that then creates a plane, because now that line has been stretched in a different direction, creating a 2nd dimension, like a piece of paper. And then you can take a 2-dimensional object and stretch it a 3rd way to create a 3-dimensional space. And if you get into really weird math, when you go into college, you can go into 4, 5, however many dimensional spaces, but those are things that we can't even really visualize in our 3-dimensional world. So the graphs of 3 linear equations with 3 variables each form what's called a system of 3 planes whose intersection determines the number of solutions to the system, or of the system. So I want to go over these visualizations really quick. First off, we have a single solution. And in a single solution situation, we have our three planes. They're acting kind of like pieces of paper. In this case, I've got the red plane, the blue plane, which is kind of cutting through it horizontally, and I've got this green plane, which is kind of also cutting vertically, but at a different rotation. And what happens is those three planes, they cut through each other in different ways, but all three of them intersect at some point right there. And that point would be our x, y, z coordinate. It could be, I don't know, 1, 3, 4, for instance. It would be exact coordinates, and that would be our single solution for that intersection. And then we also have other ways that these can interact. I could have a situation that looks kind of like a pinwheel or a Ferris wheel or a windmill, etc., where you've got three planes, just like pieces of paper, that are intersecting, but they're all kind of like spokes on a wheel. They're actually all intersecting in a line. And what happens there is that if they're intersecting in a line, what happens is that line technically is an infinite amount of points. If you remember from geometry, if I've got a line, on that line, I can draw however many points I want, an infinite amount of them. And the solution for that would maybe look something like, oh, I don't know, maybe you have a value x that can be any value, and then a value y that's maybe -2, and a value z that is 4, or maybe you have some other word combination. But basically, one of the values can be anything, at least one of the values, and the other two values are fixed values. And then finally, we have no solution. And no solution situations are situations where maybe they intersect, but never all three at the same time. Maybe we end up with a situation like this kind of weird triangular thing over here, where you got three different intersections with two planes each. This kind of T-shaped thing where the three intersections or the three planes intersect, but not all three together. Or maybe this kind of hamburger stack thing where you've got the top bun and the bottom bun, but then the middle one, which would be the patty of the hamburger, is there also, and none of them are actually intersecting. They're all parallel to each other. So in this case, none of these work out to having a solution of any sort. So we would have some triplet that doesn't exist. And in that case, there's nothing to fill in, so it can't be done. All right, that's concept one. Our second concept, which goes into our second goal, is solving a three-variable system. When we solve a three-variable system, it's a three-step process. And you'll see this in action in just a second. But step one is what we do is rewrite the linear system in three variables as a linear system in two variables. So we're going to reduce the complexity of our system from three variables with three equations. We're going to work to make it into a two variable system with two equations by using the substitution or elimination methods. And we'll talk about those as we go forward. And then once we get a new linear system with two variables, we solve it for both of those variables. So maybe I solve for x and y. I find out what those variables are equal to. Then I can take these two variables and plug them right back in to the original equations to solve for the last variable, which would be z. We're going to see this in action in a second. It's kind of a meticulous process, but it is fairly straightforward at the same time. And then our solution types, we have what's called a normal solution. So if each variable equals a singular value, like if x equals 1, y equals 2, and z equals 3, then I would have a solution like we saw above, where the system has one solution. If I have a situation that comes up while I'm solving that is nonsense, like 0 equals 1 or x equals, well, actually, I wouldn't use a variable. Where I could do that. If I have 2x plus y equals 2x minus y, and y is not equal to 0, that would result in no solutions. But typically what we'll end up with as we're solving is some nonsense with just numbers, like 5 equals 3. If I have a situation like this, which I know does not work, it's illogical, that means we've got no solutions. And then finally, we have identity situations. That's a situation where you get an equation on both sides that are the same, like 0 equals 0, or 4x plus y is equal to 4x plus y. Something that's just immediately obvious and always is going to be true, then that means we have infinite solutions. A normal solution usually is arrived at the very end. We have to work our whole way through the problem. But with a false equation, we might run into a nonsense statement midway through or even at the very beginning as we start. And same with the identity. If we are working through and we get to a point where an identity shows up, we know that it's going to be an infinite solution in that case. So let's get into it. Let's try solving a 3-variable system. So I've got a 3-variable system of equations. That means I have 3 separate equations: equation 1, equation 2, and equation 3. So what I'm going to do, my strategy here, is to either use substitution or elimination to try to remove one of the variables from my equations to create a smaller system with only 2 equations with 2 variables each. So substitution is the process of where maybe we've got, I don't know, y, let's say we've got an equation like this. This is a simple version. Y plus 4z equals 15. But I know that y is also equal to negative z. So what I can do then is I can take this information from the second equation and substitute it into the original equation. I can replace my y with a negative z. I get negative z plus 4z equals 15. That's simplified the equation because now I can combine these like terms. 4z minus z gives me 3z. 3z equals 15. And then I just divide through and I would get z equals 5. Once I know that z equals 5, I can very, very quickly go figure out what y is because I already know that y is the opposite of z. It's the negative z. So that would mean that y is negative 5. And my solution would be done. So if I have opportunities like that and I can substitute in, I can simplify my problem. In this equation, we don't have any of those nice opportunities immediately showing themselves. And generally, substitution is more bookkeeping. So there's more opportunities for mistakes. So in this situation, what I'm going to do is solve by using elimination. So my strategy with elimination is I'm going to try to use one of these 3 equations to eliminate a variable from one of the other equations. So what I can do is I can look for multiples, or I can look for singular variables. What I mean by multiples is I can look at, say, my x's. My x's are 2, 4, and 6x. Well, I know that 2 times 2 is 4, and 2 times 3 is 6. So what I could do is I could manipulate this middle equation to create either 4x by multiplying the second equation by 2, or 6x by multiplying the second equation by 3, and then subtract one equation from the other to eliminate my x values. So let me show you what I mean by that. So if I take 4x plus 2y plus 3z equals 12. My goal here is to try to eliminate this 4x. And let's change this to an arrow. I want to eliminate that 4x using the second equation, keeping this 2x here in mind. So what I'm going to do is I need to manipulate this second equation. I need to multiply it by something. So when I combine it, either using addition or subtraction, with the first equation, the x's eliminate each other. Well, if I want to eliminate 4x from this new equation, I need to somehow have a minus 4x when I combine the equations together. Positive 4 and minus 4 are going to delete each other. So what I got to do is I got to take this second equation and I got to multiply it by something. If I need to get a negative 4x, I'm going to multiply this entire equation by negative 2. I have to do that on both sides of the equation. Because remember, with any algebraic statement, if you change one side of the equation, you have to do the exact same changes to the other side of the equation, or the equality breaks down. It's no longer equal. So I'm going to distribute this negative 2 to all three values, and I'm going to multiply these together as well on the right side. What I end up with is negative 4x, negative 2 times positive, or negative 3 is positive 6x, or 6y, sorry. And then negative 2 plus positive 5 is negative 10z. On the other side of the equation, negative 2 times negative 7 gives me positive 14. So now I can take this blue equation and just put it right underneath the red equation here. And let me give these a name. This red equation up on the top is just a copy of equation number 1. This blue equation that I created is really, I'm going to call this new equation number 1. It's one of my new equations that I've created. So I'm going to take this new equation number 1. The reason why I'm giving it a number is because I'm going to create another new equation. I'll call that new equation number 2. So what I'm going to do here is I'm going to combine these two equations. I'm going to add them together. Like so. And I'm also going to be adding on this side of the equation as well. So that 14 is going to be added to the 12. So 4x and I add negative 4x, those cancel. X's are gone, which is what I want to do. And now I have 2y plus 6y, that gives me 8y, and 3z minus 10z, which gives me negative 7z. Finally, I combine 12 and 14, and I get 26. So this is my first of what are going to be two variable equations. So I'm going to hold on to this guy. I can't do anything with it right now. Just going to circle it so I know that I'm going to be using it later. So I'm going to go back to my original equation here, or my original system of equations. And now my goal is to create another new equation that eliminates the x value again. I've already used equation number 1. So now what I want to use is equation number 3, and then another multiple of equation number 2 to delete things again. So let me take equation number 2, and I'm going to write it over here in red. And equation number 2 is 2x minus 3y. Oh, not equation number 2. I'm sorry. It's late. I apologize. Equation number 3, 6x minus y plus 4z equals negative 3. And again, my goal is to get rid of this 6x. So I know that I'm going to have a negative 6x below it. So I'm going to do the same process again with that equation number 2. Because remember, the value number 2 is common to the 4 and the 6. So it's easy to multiply that 2 value to get to 4 or to get to 6. Alternatively, I could have worked with the y's in this equation because I've got a single y here. And a single y is very easy to manipulate because I can multiply it by any number to get one of these other values here. But I'm dealing with the x's. That was just a personal choice. There's not a right or wrong way to do this. So I'm going to put a line here. That was my work for the new equation number 1. I'm going to now have new equation number 2. I'm taking my original equation 2, and what I'm doing now is multiplying it by -3, because my goal is to get a -6 for that leading value. Again, I'm putting it in parentheses to keep track of everything. -3 times 2x is -6x. -3 times -3y is 9y. -3 times positive 5z is -15z. And then the other side of the equation, I have -3 times -7, which gives me 21. So I have 6x plus 9y minus 15z equals 21. Well, I can do that same thing. -6x. I can't remember my numbers here. -6x plus 9y minus 15z equals 21. Plus 9y minus 15z equals 21. And again, what I can do is I can add everything from the second equation to the first equation. And again, what happens is 6x and -6x cancel. -y and 9y become 8y. 4z and -15z become -11z. And finally, -3 and positive 21 become 18. So now I've got a second equation with 2 variables. What I'm going to do now is just build a new system. I'm going to repeat the process with a smaller system, a more simple to navigate system. So I'm going to stack these just like before, but instead of having a 3 equation, 3 variable system, it's a 2 equation, 2 variable system. And again, I'm looking for something in common because my goal is to get a single variable by itself so I can solve. Well, if you'll notice here, I've got a positive 8 on both. So I already have values that are equal. I just need to create a negative when I add them together. So what I'm going to do now is I'm just going to multiply this second equation by a negative sign on both sides of the equation. Well, the negative sign, what that's going to do, and I'll write it over here, is going to be -8y, -8y, a negative times -11 becomes positive 11z, and then a negative times 18 becomes -18. So I've multiplied that entire second new equation by -1, and now I'm going to combine that with my first equation again. So I'm adding the 2 equations together. So 8y and -8y, they eliminate each other. Perfect, that's what I want to see happen. Now I've got -7z plus 11z, I get 4z equals 26 plus -18 equals positive 8. Divide both the top and bottom, or the left and right, by 4. I get z equals 2. And that is one of my 3 values that I'm looking for. So I'm almost there now. Once I get one of the values, it all comes together quickly. Because I know that z is equal to 2, I'm just going to plug that z back into one of these 2 equations that I have. I'm going to choose this equation. So I've got 8y minus 7 times z, which is 2, equals 26. Just work out the math. I got 8y minus 14 equals 26. Add 14 to both sides. And I get, I ran out of room here, I got 8y is equal to 40. Now I just divide both sides by 8. I get y equals 5. And now I've got the second piece of my puzzle. I know that y is equal to 5 and z is equal to 2. And again, I've got 2 out of 3 of my variables, so now solving for the third is also easy. I can take this equation, let's take the first equation. I know that I've got my y value and my z value figured out. I know that y is 5 and z is 2, so all I have to do is plug those into my original equation and I can solve. I will do that. Do I have room? I don't think I do. Oh, I do. Got enough room right here. Managed to keep it all in the all in this white space this time. So remember my first equation, equation number 1 was 4x plus 2y plus 3z equals 12. But we also know that y is equal to 5 and z is equal to 2. Well, I can plug these values in really quickly. If y is equal to 5 and z is equal to 2, I've really got 4x plus 2 times 5 plus 3 times 2 equals 12. Do the math, I get a 10 here, a 6 here, and 4x stays 4x. I can combine the like terms with these guys, I get 16. So 4x plus 16 is equal to 12. From here, it becomes really straightforward. Subtract 16 on both sides. I get eliminations. 4x equals negative 4. Divide both sides by 4, and I get x equals negative 1. And at that point, I'm done. I will put my solution out here, though, because I've ran out of room. My solution then would be negative 1 for my x value, 5 for my y value, and 2 for my z value. 1 solution. And now if I wanted to be very meticulous, if I don't trust my math, I can go back to the other 2 equations, now that I know x, y, and z, and I can just plug a negative 1 here, a 5 here, and a 2 there, and see if it comes out to negative 7. Do the same thing on the equation number 3, negative 1, 5, and 2, and make sure it comes out to negative 3. That's a good way to check your work. All right, let's go to the next thing. So that's the solution of a system with one solution. So we got another one here. This one I think will be a little bit quicker, but let's see what happens. I've got x plus y plus z equals 1. 6x plus 9y minus 12z equals 14. And 12x plus 18y minus 24z equals negative 11. This first equation is fantastic because I've got a single x, a single y, and a single z, which means I can multiply that equation by anything and I can quickly solve. So what I'm going to do is I'm going to take equation number 2 this time. I'm just going to put it over here to the side. And what I need to do is I need to get rid of a variable. I'm going to get rid of y this time. I have no reason for it. I just want to get rid of y. I got rid of x last time. Well, if I want to get rid of y, remember I need to have a negative 9y. So what I'm going to do is I'm going to take my original equation for number 1, original equation 1, and I'm going to multiply it by a negative 9. I have to do that on both sides of the equation. So I can multiply through very quickly. Negative 9 is just going to give me negative 9x minus 9y minus 9z equals negative 9. And it works out very nicely because now I can just plug that equation in. And then add the two equations together. I'm not going to show the plus signs this time. Just know that you're adding these together. 6x plus negative 9x is going to give me negative 3x. Let me put this in a different color. Negative 3x. Positive 9y and negative 9y cancel. Negative 12z minus 9z is going to give me negative 21z. And then 14 minus 9 is going to give me 5. And again, I save that 2-variable equation for later. All right, so next thing. Still goes very quickly. I'm going to take that third equation, 12x plus 18y minus 24z equals negative 11. I'm going to take my first equation, the xyz equation again, and I'm going to multiply it by some number because I'm trying to eliminate the y's. So I need something that's going to give me negative 18y. Well, similar to last time, I'm going to multiply by negative 18 because I've got a singular y. So let's go ahead and put that together really quick. Negative 18 times, I'm going to put negative 18 over here as well. I'm going to fill in the blanks with my original information, x plus y plus z on the left, and a positive 1 on the right. And I get negative 18x minus 18y minus 18z equals negative 18. So I can just throw that under the second equation that I put up here, or really this is equation number 3. I can throw that under there. Let's see here. So I can throw that directly under here. Negative 18x minus 18y minus 18z equals negative 18. Oh, my handwriting's getting really bad late at night. So I put my x's together, I get negative 6x. 18 and 18 cancel, and I should be using my green color. Stumbling over my work here, guys. Negative 6x, 18's cancel because one's positive, one's negative, and then minus 24 minus negative 24 minus 18 is going to give me negative 42z, which is equal to negative 27. Well, now I've got two equations. I'm going to stack them up, create my new system. Okay, we got another weird situation here. We don't have anything that is easily multipliable like a single x, single y, single z. But if you notice, I've got -3 and -6. We know that 3 is half of 6. So if I stack these, I'm going to flip the order, actually. If I have -6x minus 42z equals -27, if I put something under it, if I have a positive 6x here, then when I combine them, when I add them together, that positive 6x and the negative 6x are going to cancel out, and I'll be just left with z's, which is what I want. So what I'm going to do is I'm going to take that top equation, which has the -3x, and I'm going to multiply it to get positive 6x. Well, to do that, all I have to do is multiply by -2 on both sides of the equation. -2 times -3 becomes positive 6x. -2 times -21 becomes plus 42z. And -2 times 5 becomes -10. I'm going to take this modified two-variable equation, and I'm just going to put it right under this one. We're going to see something interesting in just a second. If we combine these, what happens is I get -6 plus 6 cancels. That's what I wanted to do, but as you can see, we've also got two 42s. -42 and positive 42 also cancel, so the left side of the equation becomes 0, while the right side of the equation is -27 and -10 becomes -37. As soon as I hit this point, 0 equals -37, I know that there are going to be no solutions. It doesn't make any sense. As soon as you hit that point, as long as your math is correct, you can always go back and check it. But as soon as you hit a point like that, you know that there's not going to be any solutions. And I wanted to point out something here. I took a route that was actually a little bit slower. If I tried to combine equation 2 and equation 3, notice 6 is half of 12, 9 is half of 18, -12 is half of -24. So this entire left side of the equation for number 2 is half the size of this entire left side of the equation for number 3. So logically speaking, what's over here should be half the size of this. Well, you can see right away that positive 14 is definitely not half the size of -11. That doesn't work at all. So if you can notice something like that, you can immediately go, oh, there's no solution. And you're done. I did the extra math because I wanted to show you this process, and not always will it be so clear. All right, let's try one more. 3-variable system, again. This one's very interesting because I've got 2x minus 2y plus 2z equals 12, 10x minus 2y plus 10z equals 60, and then the third line looks almost exactly the same as the first. 2x plus 2y plus 2z equals 12. Well, that's kind of interesting. That means, at least to me, if I see something like this with equation 1, 2, and 3, I'm going to pick 1 and 3 to start with. I'm going to take equation 1, 2x minus 2y plus 2z equals 12. And then equation 2, or equation 3, I'm going to try to get rid of a value here. Now, I would normally, if I was doing examples, I would normally try to get rid of z just because I've gotten rid of x and y, but the variables are just the variables. It doesn't really matter. Notice these are opposites. 2y and -2y are immediately opposite each other. So I'm just going to add these two equations together really quick. So 2x plus 2y plus 2z equals 12. If I add these together, I get 4x. Oh, I should use a different color. I get 4x, -2, +2, cancel each other out. Great. 2z and 2z gives me 4z. and then I get 24. Step closer, let's stick that on the back burner. We go back here, that was a really fast one. Well, I've got another really fast one because the second equation also has a negative 2y, which can be combined with that positive 2y. So again, I get a very, very quick equation to deal with. So I'm going to take that second equation, 10x minus 2y plus 10z equals 60. And then my third equation, I'm just going to stick it underneath again. 2x plus 2y plus 2z equals 12. If I add them together again, I get 12x, these guys cancel, plus 12y, or 12z equals 72. So that's my second equation. So my new system is going to look like this. 4x plus 4z equals 24, and 12x plus 12z equals 72. Well, I'm trying to eliminate another variable. I've got 4's on one equation, 12's on another. Well, I know that 4 times 3 is equal to 12. So if I multiply the first equation by negative 3, I should get some new value here. Or I should get an equation that'll work nicely. So I'm going to stick this guy up top. 12x plus 12z equals 72. My goal is to get a negative 12. So what I'm going to do is multiply by negative 3 on both sides of the equation. (4x plus 4z) and 24. Well, you'll see when we multiply this all together, we get negative 12x minus 12z equals negative 72. Well, that's interesting. That means if I stack these, if I stack that orange equation that I moved over and this new red equation, I get this situation. And if I add them together, 12 and negative 12 cancel. 12 and negative 12 cancel. 72 and negative 72 cancel. I get 0 equals 0. I don't have to continue any farther at this point either. It doesn't really matter what x and y are. I've got infinite solutions. And I'm done. So in this section, we did a lot of manipulation of these equations. Just remember, the goal is to go from a 3 equation with 3 variables system to then work towards having a 2 equation, 2 variable system, and then use that to solve for x, y, or z, like I did. Let me go back up here. 3 variable system to 2 variable system, and then eventually I solved for z. Once I had z, I plugged that z value back into one of these 2 equations right here. I did it on the first one. I do this work and I find my y value. Once I have my y and z value in this situation, I plugged y and z right back into the original first equation. I did that all over here, and I solved for x. Once I had x, y, and z, I had my solution. So we follow that process. So we either get to one solution, we get to a situation that breaks the equation, no solutions, or we get to a situation that's always true, 0 equals 0, or x equals x, or 3 equals 3, or whatever, and that's going to be infinite solutions. So that's the video for 1.4. I hope it was informative, and we'll be going over questions on this section later on next week. Have a good day.